Hi everybody, I'm the greatest living inventor, and today we are doing my invention, photographing inside a black hole. So let me write it down. Photographing inside a black hole. Okay, so it looks like it's only 4 pages, but it's the second time that I'm recording. It takes long to explain everything, so I'll just rush it even though it's only 4 pages. Okay, so I'm just taking off my jacket. Okay, so based on the first, I'll just close the air conditioner also. Okay, sorry. Based on the first lecture in the course about black holes of the teaching company, TTC, today they are called the Great Courses, TGC. I'm like a great fan of them. I watch all their courses. If we are standing on planet Earth and throw an apple upwards, okay, so I don't have an apple, so I'm doing this with a tomato. Okay, I hope I don't drop it on the floor because I'm not that good with throwing and catching. Okay, so it's going up fast, and then it slows and slows and slows until it stops, and then it's falling back down. You know this, of course. So if we're standing on planet Earth and throw an apple upwards, the apple will fall back down. Let's suppose we could throw the apple faster than the escape velocity. Okay, escape velocity. Okay, this is the speed that you need to move, to fly, in order to upwards, in order to break free, to escape from the gravity of Earth. If you are moving slower, then you will fall back down. Okay, we are not Superman. We cannot throw the apple so fast, so it falls back down. But if we could throw it like in the escape velocity, this is the speed that a rocket that is going to space is flying. I think it's 11,000 kilometers per hour, something like this. Okay, so there is an escape velocity. So let's suppose we could throw the apple faster than the escape velocity, then the apple could have exited from Earth. The escape velocity is different according to the mass of the Earth and the height that we are in. Okay, so the higher we go, the less speed, the less velocity that we need. Velocity is just another term for speed. It's speed with direction. Okay, the speed that is enough, the speed that is enough, sufficient for escape when we are already high in the atmosphere, is smaller than the speed that we need when we are on the surface of the planet. Okay, if a bird is trying to escape, it needs less speed. The escape velocity is, okay, if you are almost escaped, then you need much less than this is important in the invention. Okay, the escape velocity is named after the greatest speed that is needed on the surface of the planet. Okay, so if we have the Earth, okay, I'm not drawing because that's what I did before, and this is why I was left without time. But the escape that we need down here on Earth is the greatest. Up there in the sky, it's lower. When you're on the boundary of space, it's even lower. It's very, very small. So it's like, and here it's very, very big. The speed that we need to escape the gravity. Okay, so the escape velocity is named after the greatest speed that is needed on the surface of the planet here. Okay. What if we were able to, each time that the apple slowed its speed a little, to increase it again? If we could, for example, give the apple a push in each meter that it's getting up, the apple would not lose its speed. It would be able to escape from Earth. Okay, so for example, okay, let's imagine it. Okay, let's not imagine it. I'm just reading because I will not have time later. For example, if we had a mountain, and in every floor of the mountain, it's like floor like of a building, a story, tier, level, in every floor of the mountain, so-called, let's say every 1 meter, there was a teeterboard. Okay, teeterboard. It's one word, sorry. Teeterboard, Korean plank, like a seesaw or teeter-totter in a playground. Okay, so Korean plank. Okay, it's like we have this fulcrum and we have a piece of wood, a plank. And here there is somebody, and here there is another somebody. And if this person jumps and falls, then this person, if this goes down, this goes up. And this person flies into the air, and then he falls, and then this goes down, and this goes up, and this person flies, and so on. Okay, so you can see in Wikipedia teeterboard, and you can see which is the Western version in the circus to the traditional Korean sport Neol Twiggy or Nol Twiggy. In Wikipedia, Neol Twiggy. Okay, so this is the Korean sport. Neol. Okay, so you can see it in Wikipedia. This is the Korean word for the same thing. They invented this. Okay, and let's suppose, so remember what we were saying, I'm erasing everything. So now we put a teeterboard on each level of the mountain, on each floor. Of course, we are not talking about real, this whole apple thing is a metaphor, okay? I'm explaining the idea. Then we are talking about the real thing, which is photons, particles or waves of light. Okay, you know that each photon is also both particle and wave. Okay, so so we have a mountain. Okay, this is the ground, this is the mountain, it looks like stairs. Okay, and we have on each floor we have what it's called, teeterboard. Okay, so this is a teeterboard. And this is a teeterboard, and this is a teeterboard, and this is a teeterboard, and we have all the way up. And here we have our apple. Okay, so this is the apple. This is our original apple. Okay, why am I saying original? Because there are also other apples that are dropped from a helicopter. Okay, there is a helicopter that is dropping apples. Okay, let's draw a helicopter. And it's dropping, can you see this color? Yeah. Okay, so these are more apples, another apple. Okay, this is how to see. I will not write in pink. Okay, so this is another apple. And the helicopter has a whole sack of apples. It has a lot of apples. Okay, so this apples comes down here and drops on one side. This goes up. Sorry, this goes down. This side goes down. This side goes up. And this apple, the original apple, is jumping. Okay, after this drops and hits this side goes down. The other side goes up, and our apple is jumping to the next teeterboard. Okay, so and after this the helicopter is moving to here and drops another apple. Oh, sorry. Another apple. And okay, this is the helicopter after a while. And this apple, this side goes down, this side goes up, and the original apple is jumping to the next teeterboard. Okay, like this. Okay, so the original apple jumps and jumps and jumps and jumps, and in total the original apple gets up all the way towards space and escapes the Earth. Okay, so I'm reading to you, but now you have the picture. And let's suppose that, okay, so for example, if we had a mountain and in every floor of the mountain, let's say every 1 meter, there was a teeterboard. And let's suppose that up above we have a helicopter hovering above all the time with a sack of apples. And the helicopter drops down on the teeterboard once in every fixed time, let's say once every 1 second, a new apple. 1, 2, and so on. It drops, and it drops, and it drops. Okay, and our original apple starts at the height of the surface. Okay, this is the ground level. Ground level. Waiting inside the first teeterboard. Then in exchange for another apple, the pink one, that falls from above, the original apple rises up 1 meter, okay, to here. And now our original apple is waiting inside the second teeterboard. And then in exchange to another apple that falls from above, the original apple rises up another 1 meter, and now the original apple is waiting inside the third teeterboard, and so on and so on. Okay, that was the metaphor. And now from the parable to the moral, to the lesson of the story. Okay, to the real thing. So let me erase this. But you get the picture. Like with a small speed that you keep pushing up, you can escape something that looks like impossible at first. Okay, excuse me. Sorry. So let's suppose we are shining a light with a flashlight in a short flash directly downwards toward the black hole. Okay, so we have the black hole. And we have a flashlight. And we are making a light. This makes light. And the light goes down towards the black hole and hits the ground of the black hole. Okay, there is an event horizon. Okay, this Okay, this is the event horizon. Okay, and we cannot see what happens if we stand here. We cannot see what happens when the light gets to the ground of the black hole, to the ground level, surface of the black hole. But from the point of view of the light, if we were the light, we would die because we would get spaghettified. But for the light, this doesn't matter. It gets more energy because it's pulled fast. But it's going here and it doesn't feel anything here special and until it hits the ground level of the black hole. For us, from here on, we don't see the light. Or we see it very dim and slow. Let's be more accurate. Until we don't see it at all. Okay. So, if the light is exactly perpendicular, okay, exactly 90 degrees, this is the surface of the black hole, and this is 90 degrees perpendicular. If the light is exactly perpendicular, it manages to enter without any problem, and also to get down and hit the ground of the black hole. Part of the light is reflected back by the object that the light hit. Okay, so this is the reflected light. This is the original. And this is the reflected. Light. Okay, but the reflected light is losing energy because the black hole slows it down, like it's like the Earth slowed down the apple, okay, or the tomato. Part of the light is reflected back by the object that the light hit, by this, the ground of the black hole. And now there is reflected light that is trying to rise up. Can you see the orange? Yeah. Okay. That is trying to rise up. This light that is trying to escape from the black hole cannot slow down because light always travels, moves at the speed of light. But it's losing more and more energy, like shift to red. There still is a photon, a light particle or wave, but it's losing energy, so it's vibrating in a lower and lower frequency. Okay, so it's getting from orange to red. And then it's getting invisible for us, and then it's gone. Okay, if we don't help it. Okay, I'm not explaining the red part. If you want, like only in 1 minute, there is the color of the light. If it's purple, you know the colors of the rainbows, there are purple, it's called violet. When you talk about light, they usually say violet. And it's getting all the way towards like blue. It's not so squiggly but longer light waves, okay, blue, and so on, until you have red light, which is very long, okay, red. Okay, so let's say in some time, okay, let's say this is 1 second. Okay, so in this part, this is the how many waves we have here is the frequency. Okay, so you see that here is a high frequency. Sorry. High frequency. And in the red, it's low frequency. And what you need to know, okay, because in the same time, okay, if we take this and put it here, like we have a half of the wave. This is a whole wave, and this is half. Okay, and here we have like, I don't know, 3 or 4 waves in the same time. So this is high frequency, and also high energy. It has a lot of energy, and this is low frequency. And the more we go to the low frequency, the more we lose energy, and we have low energy. The frequency and the energy is going together. So this is high energy with high frequency, and this is low frequency and low energy. Okay, energy and frequency for us, it's the same. So anyway, the more you have low energy, the more you go towards the red. So at first, this is some color, and then it's going towards the red. Okay, so I'm not explaining this deeply, just to give you a hint. If you want, you can look it up. Okay, 28 minutes. Okay, we are still on the first page. That's what I meant, that it looks like 4 pages, but it's long. Okay, so okay, so I'm reading again the last paragraph. This light that is trying to escape, the reflected light that is trying to escape from the black hole, cannot slow down because light always moves at the speed of light, but it's losing more and more energy, like a shift to the red, and there is still a photon. Photon is a light particle or wave, but it's losing energy, so it's vibrating in a lower and lower frequency. Okay, so it's getting red, and then it's getting invisible for us. We lose it. Okay, so that's what it means, that the light cannot escape the event horizon. Okay, this is the event horizon. It's like the atmosphere of the black hole and some boundary, and it's not a good image because there is nothing there. But it's like some point where the light, without any help, cannot pass back, so everything here is trapped if we don't help it. Okay, if we won't help him, at first the reflected light close to the ground level is, for example, blue, and okay, so at this, let's say we shine, instead of orange light, we shine blue light. So this is in the beginning, this is blue. I'm doing the same with blue. This is the shined light that we shine, and this is the reflected light. Reflected. Okay, so if we won't help him, if we don't help him, at first the reflected light close to the ground level is, for example, blue, then it loses energy and it becomes yellow, then red, then infrared, then radio waves, and then it's impossible to recognize it at all. It disappears. Okay, this is like the continuation here. It's radio wave, infrared, and radio waves, and so on. Okay, but what if we would help him? What if we would help him? So now, yes, we are helping. In each time, if each time we could give it a push towards a higher energy level. Okay, so here, instead of letting it go to the red and then disappear, we would push it back so it's blue also here. So, but what if we would help him? If each time we could give it a push towards a higher energy level, which means making it more towards blue, then it can reach all the way upwards and escape the black hole. How do we do this? We need to use second harmonic generation. Okay, so second harmonic generation. You can see this in Wikipedia. Wikipedia, second harmonic generation, which you can see in this video by the Thought Emporium. Okay, so I'm giving you the link in the description of this video. Make lasers change color. Make lasers change color. Change color. Okay, so this is an important video that you can see. DPSS lasers and second harmonic generation. Frequency doubling. Okay, so even if we don't know what second harmonic generation is, Now we understand intuitively what is frequency doubling. It's taking a low frequency and making it twice as high. Okay, like from this making it into this higher frequency, or from this making it into this. Okay, so changing the colors. Make lasers, change color. Laser is just a light with the same color, and all the light waves are going in the same direction. Okay, so now I'm reading you from this video description. With powerful enough lasers, the world starts behaving very differently. Using a nonlinear optical process called second harmonic generation, you can merge merge into one. You can merge pairs of photons in a laser beam to create a single photon with twice the energy. This means that one color of light is turned into another. Okay, we take two of this and make one of this, for example. Okay, so if we have a few photons that are hitting here, we have half of the amount here, but it will be in a stronger color, in higher frequency color. Okay. If we can do second harmonic generation in here, and then in here, and then in here, and so on. Okay. This means that one color of light is turning into another. Okay, so this is the description of the video. Now we are continuing. In practice, this is done with infrared lasers. I'm sorry, this is still the description of the video. In practice, this is done with infrared lasers, which, when shot through a special crystal, merge to form a color like blue or green, depending on the setup. Okay, so they take infrared, even more red than red, more low than red, infra means below, and then making them into blue or green. Okay, but they are using a crystal, okay, a special rock. Okay, we don't use anything because we don't have, not anything, but we don't use anything like matter, because we don't have the ability to sustain matter here. It will just fall into the black hole. Okay. So, but we cannot hold a crystal in there. It's inside the black hole. So what can we hold there? More lasers. Okay? More light. This is good because in nonlinear optics, in Wikipedia you can see nonlinear optics. I'm reading to you. The nonlinearity is typically observed only at very high light intensities. Values of atomic electric fields typically 10 to the 8th volts per meter, such as those provided by lasers. Above the Schwinger limit, I'm reading and then I will write Schwinger limit. Above the Schwinger limit, the vacuum itself, okay, the vacuum, here is a vacuum, here is a vacuum. The vacuum itself, the space, is expected to become nonlinear. In nonlinear optics, the superposition principle no longer holds. Okay, now what does it mean? This means that if you have, okay, this is now not from Wikipedia, this is my explanation. This means that if you have a strong enough lasers, two lasers, cutting each other at some point, okay, then the space itself begin to act like that crystal that we need and scatter the light like a lens. Okay, so it's not really like this. This is a superposition that they pass through each other, and in this point there is momentarily something bigger. So no, it's like this. It's like they stop here and do something special here. Okay, so this is in very high intensities of laser, like here, they behave like this, non-linearly, and they create a lens. Okay, so we create a lens. Okay, and this is the important part. This means that if you have strong enough lasers cutting each other at the same point, then the space itself begins to act like that crystal that we need and scatter the light like a lens, which means that that point no longer obeys the superposition principle, this principle, which means the lasers do not ignore each other if they are very, very strong. Okay, they get to this point and they do the lens there. Okay, you can also read this here, 2 photon physics in Wikipedia again. I'll write it here. 2 photon physics. Okay, so 2 photon physics. Photon is a wave particle of light. In pure vacuum, I'm quoting Wikipedia, in pure vacuum, okay, here, not here, but here and here, outside the event horizon and inside the event horizon, but above the ground of the black hole, in space and in here. So in pure vacuum, some weak scattering of light by light exists as well. Okay, so one light scatters another light, or another light that is coming, which is this. This effect, okay, now my explanation, based on Wikipedia. This effect also protects us from gamma ray bursts that come from halfway across the universe. Quoting Wikipedia, an analogy would be light traveling through a fog. At near distances, you can see a light source more clearly than you can at long distances, due to the scattering of light by fog particles. Similarly, the further a gamma ray travels through the universe, the more likely it is to be scattered by an interaction with the low energy photon from the extragalactic background light. Okay, this is the end of the quote. Now my note. They interact, okay, these strong gamma bursts, which are like the lasers. They interact even if they are not in the same direction. This is important because in our case, they will definitely will not be. One photon will come from the ground of the black hole, this reflected light, and one photon will come from above, from our camera spaceship. Okay, it will come like from here or from here. Okay, from our, this will be our camera spaceship. Okay, let me erase this and make it again because it's very crowded now. And I will not draw the whole black hole, just this part, okay? Okay, and I'll drink something. 46 minutes, I really need to hurry. Okay, so just the sketch, we have the black hole. Okay, this is like the ground. And we have the event horizon. And here we have our camera. I don't know how to draw the camera. Let's draw it like okay, this is our camera. Only without the flash, because the flash will be the lasers that come from the sides. Okay, so this is our camera. Okay. Okay, so note, they interact even if they are not in the same direction. This is important because in our case they will definitely will not be. One photon will come from the ground of the black hole and one photon will come from the above, from our camera spaceship. Okay, this is our camera spaceship. Of course it can be robotic, not with people. Okay, so in our case the low energy photon will be our picture that we want to photograph. Okay, this light that is coming back that we want to photograph, the reflected light from the ground of the black hole, and the strong gamma ray will be the laser. Okay, these lasers that we shoot from the sides. Okay, so how is this actually done? First of all, in order not to fall into the black hole, the whole spaceship, our camera, is put into an orbit around the black hole so that we follow the same spot on the black hole. Black holes are rotating. Our spaceship is outside the event horizon in a safe distance. Okay, so geosynchronous satellite. Geosynchronous satellite. Okay, in Wikipedia. I'm not explaining how a geosynchronous satellite is working. You can see it in Wikipedia. First of all, I read this, sorry. How do we know the speed and direction of the black hole rotation? Okay, the black hole is here. How do we know how fast it goes? We cannot see the black hole. My method of photographing works only with black holes that are not feeding. Feeding, it means accretion disk. So my method works with black holes that are not feeding, that do not have an accretion disk right now. But we need the black hole to be feeding accretion disk in order to measure how it's rotating. So the solution is to feed it a little bit. Just to measure the X-ray from the little accretion disk that we created. And soon after that, this temporary accretion disk ends and we can take the photograph. Okay, I'm not explaining how an accretion disk forms. It's basically the black hole sucking material from something like a star or something, a gas cloud, and it hits in this rotation and friction inside the gas, and it gets hot, and this is how we see something there. This picture that you've all seen of a black hole is a picture actually of the accretion disk. So my invention is a real picture of the real black hole, not the accretion disk. So my invention cannot show. It doesn't work. It's very sensitive to light, and if there is an accretion disk, it's too shiny, too bright, and to use my invention. But we give it a little food, like a little gas, and then we calculate how it's rotating, and then this gas disappears, and we have no accretion disk, and we can take a photograph in my invention. Okay, so think of a big cross sign, like Christians bless Father, Son, and the Holy Spirit. I hope I do this right. Okay, so a Father like head, Son heart, Holy one shoulder, and Spirit another shoulder. And we have the long vertical axis, which on one side, head, will be the light detector, which is our camera. Okay, light detector. So imagine a big cross. Okay, we'll do the cross in, let's say, in blue. Okay, so we have this cross. Okay, this is the cross. Okay, so we have the long vertical axis, which on one side, head, will be the light detector, which is our camera, and on the bottom side, heart, will be the ground of the black hole. On both sides of the short horizontal axis, of the cross, shoulders, will be the flash of the camera. Okay, the flash here we have flash. Okay, and also here. Okay, this is like the flash, giving light. Remember, like the flashlight. Like a camera has a flash, so this is the same thing, but it's lasers, strong lasers. Okay. the strong lasers that light up the point that we want to photograph. And also they light points above it in special intervals along the long vertical axis of our cross. So first of all, this light comes together. Okay, this is coming together because of the symmetry and that they fall in the same acceleration. It's like you can see in Wikipedia in physics there is the hunter and the monkey. Okay, which is similar. They fall, the bullet is falling or the arrow is falling in the same way as the monkey. So here also it's working by this falling in the same way. So they meet together. Okay, and this shoots one ray of light to here, and also more ray of lights upwards and upwards and upwards. Okay, this works with mirrors. Okay, there are many mirrors here and the beam splitter that splits the laser. So in the same second there are a lot of lasers eventually that each meets each other. This one meets, this one meets, this one meets, and this one meets first, this one meets second, third, fourth. Can you see the idea? Okay. So and also the light points above it in special intervals along the long vertical axis of our cross. The rays of laser shoot from like the blades, slats of a hand fan. Okay, like a fan. Okay, like that ladies used to use a fan before there was an electric fan. So it's like a hand fan. Hand fan. Okay, why hand fan? Because this has mirrors, okay, and the mirrors split this beam that is coming. Let's say there is a beam, and the mirrors split the beam to many lasers, not in the same direction. And here also the same. Okay, it's lasers, but one is pointed this way, one is pointed this way, one is pointed this way, and so on. And they meet. This one meets this one, this one meets this one, this one meets this one, and so on. Okay, from the center of each shoulder, okay, the rays of laser shoot from the light from like the blades, slats of a hand fan, from the center of each shoulder. This is a shoulder and this is the shoulder. The pivot of the hand fan towards the long vertical axis and meet in the midway, here and here and here. If we could see the rays of lasers, then each shoulder will look like the highest point of a side spar cable stayed bridge. What's the time? 59 minutes. Okay, I need to hurry a lot, so I will write just the name of the bridge. Side spar cable stayed bridge. Okay, so this is what these rays look like from a common center. And this is the actual bridge that the cars go along, and the people. Okay, and the other shoulder will be like its reflection in the water. Okay, exactly the same. The road on which the cars are traveling, that is hanging in the air above the water, will be unified with its reflection. So it's just one axis here to both bridges. This is a bridge and this is a bridge. Unified with its reflection, and it will be where the powerful lasers meet. And also along this road, the photograph result will travel from the heart down in the black hole upwards towards the head, our camera light detector, which is furthest away from the black hole. Okay, our spaceship. Okay. Eventually, all the lasers coming from each shoulder will be projected from the same laser, which will be split and directed with individual adjustable mirrors. But at first, we start with adjusting the mirror that is responsible for the uppermost beam. Okay, this one. The uppermost beam, the beam that is furthest from the black hole. We project this first beam and its counterpart from the shoulders and lower them using the adjustable mirrors until the beams meet just below the event horizon. We would know this because there is light just over the event horizon, which so far almost could gotten out. Okay, there is some light here, and if we give it help, it can jump to here. Okay, like the tether board. We can push this light that is almost here to outside of the black hole, of the event horizon. So suddenly this will detect light. The light detector will detect light. Okay, I will just read it fast. We project this first beam and its counterpart from the shoulders and lower them using the adjustable mirrors until the beams meet just below the event horizon. We would know this because there is light just over the event horizon, which so far almost could gotten out, but couldn't because nobody helped it. But now we help it with our lasers, so we will suddenly detect a light coming out of the black hole with our camera, the light detector. Then we fix these first mirrors. This is the first link in our chain of amplifiers. And we go on to set the next amplifier until we have more light in the camera coming now from both amplifiers, and so on until we reach the bottom, the ground of the black hole. Here there will be a lot of light because our lasers will actually heat the temperature of something, and this something, the ground of the black hole, will emit light. Everything, no matter its color, when you heat it, emits some radiation. It's called black body radiation. In every link in the chain, we do a process similar to tuning your favorite station on the radio. We play with the knob until the signal gets loudest and clearest. Only here, instead of sound, it's light. So now with all our mirrors in the right angles, we shoot a laser in all of them and measure the time it takes for the light to reflect from the ground all the way through the light amplifiers to the camera. This time gives the time it takes to go all the way to the camera, from the moment we light to the moment it gets to the camera. This time gives us an idea of the height of this spot on the ground. This is just like LiDAR. LiDAR, like a radar from laser, you can see in Wikipedia, LiDAR, but instead of measuring an ancient city hidden in the rainforest, we are measuring the topography of the ground of the black hole, one point at a time. Note, when you get to 1.5 Schwarzschild radius, there is the photon sphere. Photon sphere. It's like another layer, but I think the photons there are not as powerful as our lasers, because our lasers fall with the black hole gravity, while the photon sphere light is on the same level all the time. If the photon sphere just blurs the picture, then we can take the average of a few photos. Okay, so I hope it will record. That was my invention. I hope it was clear, and I'll see you in my next invention. So thank you very much. Goodbye. Thank you.